Let me just move to that part right now. And so it looks like this. Tools, tools, tools. Let's make it really big. All right, so here we are. So, so this course is broken down into a lot of little lessons that are going to help you with your overall assignments, just like we've done in the past. One thing you're going to note immediately is that there is no midterm tests. So midterm tests, goodbye, they're not there. What they've been replaced with in this course, midterm and even final exams, are regular labs that we're expecting you to go to, right? So that's what's kind of happened. It's more of a practical approach. So no true, false, multiple choice, no Q&A that you're going to do on a test. We found that doesn't do much in terms of your understanding of how to program physics. You might understand physics, you might be able to do an equation, but who cares, right? It's more of, can I program it? So that's why you're going to see a series of labs. And what that means is, if you look at the course outline, is that we're going to mark you on the best 12 out of 14 labs that's going to be happening, right? So you can see that there's 12 that are postmarked. You're going to be using our SDL engine. Okay, there's no other option for using something else of your own, and there's a reason for that. Not that it's the easiest thing to use or it's the smoothest engine. It's not really an engine, more like a framework that we're using. It's really an assignment framework for you to use. So the expectation is that you're going to dive into it and use it this semester. Some of you had some mixed results the last time, and we're going to continue to use it this semester because you know it. The other thing is, when it comes to preparing labs, one thing to note is it's hard for us to kind of whip up, kind of an engine just for that lab and then say, here's something very, very simple and get it going and make it work and all that kind of stuff. So that's why we have the framework in the first place. So please embrace it this semester as much as you can. Assignment 1, 2, 3, and 4, again, it'll be required that you submit programming, and there will be some questions related to physics that you're going to have to answer. Sometimes it'll be in the form of some problem questions that you're going to have to complete with you and your partners. So the assignments 1, 2, 3, 4 are all partner-based. All right, so you and a partner. Some people like to work alone. I work alone. But the reality is that you're going to have a lot of time to work alone on your labs. Every single lab is individual, right? So it's going to prove out, do you know how to program, okay? So I fully would ask, if you can, to partner up with the people that you know are good workers, that you know, I know people are smiling and they're like, yeah, there's some people that aren't such good workers. You're right, people, everyone does things and they're here for different reasons, right? So if you know someone, people that you're probably sitting with right now that you know work well, partner with those people. Don't partner with the rando, okay? We don't want that kind of stuff to happen. That's not really cool. And that's what you want to do for assignment 1, 2, 3, 4. Notice that the assignments are incrementing in value, so 10 for the first one, 12, and then 15 for the last two. But take a look at that lab portion. It's worth 48% of your final grade. And I'm telling you this the first day because, in the past, if you show up to a lab or you miss a lab, who cares? Please don't do that this time. Each of your labs is worth 4% of your final grade. It's like a mini assignment of its own. So you need to be there. They're going to be fairly straightforward. The professor's going to walk you through them. Okay, it's not like it's going to be something that you're going to have to come up with out of the top of your head. It's not about that for you. What it's really about for you is getting there, practicing, and getting a hands-on approach to understanding how to code C++ and kind of do your physics stuff in the labs. So that's what's happening there. In the first half of the semester, it's all around the fundamentals of physics. So what we're going to get is, starting today, geometry and trig review. What is geometry? What is trigonometry? Do you need to know calculus for this course? In the past, some iterations, before, we had calculus in this course. But what we found was programmers didn't use calculus. They kind of looked at it and go like, why, Tom? I don't know how to incorporate calculus. And the reality is, from a game perspective, you probably don't need it. If you're going to do some kind of physics simulation, which is a very different thing than making a game, then maybe calculus is a good thing to know. If you want to enrich yourself, and maybe do physics in the future. Maybe you make your own physics engine. Calculus might be a good thing to do, right? But for this course, because it's a fundamental course, calculus is not here. However, you do need to know about triangles. If you don't know about triangles and you're leaving this course and you're doing things like OpenGL or other kind of drawing things, whatever you're going to do, triangles are the basis for movement in a 2D kind of space and 3D space. You need to know about triangles. So we're going to talk about triangles today. We're going to go then into motion in one direction for a couple of weeks, next week and the week after. And motion in one direction means I'm going to use some kinematic equations over one dimension. We're going to expand that into 2 dimensions over the following 2 weeks, and then we're going to get into the laws of motion. And really, there's Newton's 3 laws of motion, right? What are Newton's 3 laws of motion from high school? Anyone know? Can anyone remember? Yes?
I know one.
He knows one. Go ahead.
Every reaction has an equal and opposite reaction.
Okay. For every action, there's an equal and opposite reaction. I like that one. What about you? Yeah.
Objects stay in motion.
Sorry?
Objects in motion stay in motion.
Objects in motion stay in motions. Objects at rest stay at rest. That's the other one, right? And there's one more. Right, what's the other one that we're missing? It's actually not really a law. It's more like a formula in many ways. Force is equal to mass times acceleration, right? We're going to know those things. Those are the 3 laws of motion we're going to go over in weeks 6 and 7. In the second part, we're going to be talking about energy, potential energy, and all those kind of things, and solving equations with energy as opposed to using the 3 laws of motion in kinematic equations, right? Again, kinematic, if you think about what that word means, it's like motion equations, right? Instead of using motion equations, we're going to use energy and talk about potential energy, kinetic energy, all that kind of stuff in the weeks 9 and 10. In 11, 12, 13, and 14, those last 4 weeks before our final special topics that's coming up on week 15, where we may do things like particle systems or something else. We'll see how it goes, how the semester plays out. We're going to be doing 2D collisions in weeks 11 and 12, and weeks 13 and 14 is collision response. Now, you've done collisions, right? And the game engine that we're giving you, the little engine we give you, has a collision manager. So why are we going to be talking about 2D collisions, at all? And where's the 3D portion of this thing? Are you going to get 3D from this course? The answer is no, right? In the past, we have had a 3D component to this course, but what we found, it was too complex. It's a lot, and what ends up happening is we're moving at a breakneck pace before, and so what we've done this semester is slow things down. The 3D component, there's a whole other course after this one that's going to happen next semester, and we're going to port all the 3D components to that course, right? So you're going to be using something like Unity to do that. All right, so that is the course outline. Any questions around the stuff that we're going to be doing this semester? Again, one thing to note is all of this is happening with C++, okay? So there is no other language we're going to ask you to know. You're going to be using Visual Studio 2022, right? So if you don't have Visual Studio 2022, please get it as soon as possible, because that's the platform we're going to be using, and it's all going to be in C++. Okay, so that's your course outline. And again, one more time, I just want to go back to the evaluation scheme. So if you notice how this works out is the first 2 assignments are all going to be about the laws of motion, motion in one direction, Newton's laws, all those kind of things. And the last 2 assignments are going to be on collision detection and response. Okay, that's how it's going to be broken out. All right. One thing that we're going to continue to do excuse me, is assignment videos. And you're going to say, well, why assignment videos if we're in person, right? Because then you can verify. We use assignment videos during COVID, the peak of COVID, because I didn't know who you were, right? I never met you physically, who is this person that's submitting this stuff, right? But now we're going to continue to use assignment videos for a couple of reasons. One, you may not show up. We don't know what's going to happen. There's still some uncertainty. Although the government's telling us that, hey, you don't need to isolate for 5 days and all that kind of stuff, we don't know what's going to happen this semester. And so to be safe, we're going to continue with the assignment video stuff this semester for sure. I think it's good anyway because what it does for you is it gets you to practice, talking about your work, which is a good thing, especially when you're doing an interview. I think if you're ever going to talk to any kind of prospective employer, they're going to ask you things like, so, talk to me about your work. Talk to me about how you did this. And this is what the assignment videos do. This is why I'd asked that. In the past, I'd said it's okay for you to just do it by yourself. But if you're working with a partner, maybe you want to trade off. Maybe half of it you want to do and then give the other half to your partner to talk about. So both of you can get experience on how to talk about your what you're kind of coming up with. All right, so that's assignment videos. We also have one thing that's new in this course, and you've done this in your when you were with us in AI, is lab reports. So every lab that you're going to do is going to have a report that's going to be pre-made for you to fill out. Remember that the lab report is there as a checklist for you. So the checklist for you is going to be something that you can use to say, okay, I got this part done. Please make sure you submit your lab report and show your lab report in your assignment video when you submit it. Okay, so remember, assignment videos are not just for assignments, 1, 2, 3, 4, but they're also for your labs that you're going to do on Thursdays. The expectation is when you're there on Thursdays, you can finish most of the tech. So anything that is asked of you to do, you can get it done, like in class. So please arrive early. Make sure that you're prepared with your laptop. Bring your charger. Have all that stuff ready to go. I know this is a new thing. You probably have some kind of rig at home, or maybe you have your laptop was at home and everything was charged, and you forgot your laptop battery today and all that kind of stuff. Guys, be prepared because it's important you get it done. You don't want to do it over again. And what I mean by that is use your time wisely. If you're in lab and Joss is going to go over stuff with you, for the most part, the labs are geared and measured so you can get it done within that 2-hour period. All right, so it doesn't make sense for you to go to the lab, not do anything, go home, do the lab again, and then watch videos. It's just inefficient. You have a lot of stuff happening this semester, and I recommend being as organized as you can as a success strategy. Okay, any questions around this stuff before we go on? Yes? What? There are, but let's face it. I mean, do you have Visual Studio 2022 hooked up on your machine? Do you have a machine? Yeah. I recommend it. Why? Guys, we're all developers, right? And if I'm going to go somewhere and work, I should be able to work anywhere. Why the heck would I depend on a lab for my stuff? Sure, I mean, worst case scenario, if you forgot your computer at home, you can still work. Guys, get yourself your laptop. You're going to need it, right? And work on it. Develop your environment so that it's for you. You turn it on, you've got all your tools ready to go. Why would you depend on your lab? I think that's the worst case scenario, not a great scenario. Not at least in my opinion for developers. Any other questions before we run? Yeah. The Wi-Fi. Yeah, I know it's kind of a weird thing. It's the Wi-Fi is right here. Did you get the password? That's the password right there. Right? So it's the George is what you're connecting to. It's a weird thing. I don't know why it's not called GBC, but it's there. I know, he's grabbing me too, right? Because he's like, where's that password? There it is. All right, any other questions? Guys, I'm super excited to be with you guys this semester. We're finally in person, right? It's like, I was listening to the radio today and they were like, back to reality. Yeah, it's back to reality. Bit of traffic though, I can tell you. All right, let's talk about geometry and trig. And I'm just going to go really quickly and do a bit of a review on what geometry and trig is about. And you guys should remember what geometry and trig is anyway, but let's do this. So I want to talk about a few things, and very simple stuff, guys, right? What are angles? What are triangles? How do we do calculations with triangles? How do we do these things? And I'm just going to bring these out right here. Now remember, what if, you want to refer back to these notes in the future. I'm going to put the PowerPoints on later on today. That's what you're going to see. They're going to come up online. And the other thing that you're going to also see today is this recording is going to be inside of your week 1 content area. So every time we get together, there's going to be a recording, worst case scenario. I believe Joss will also record everything as well. So worst case scenario, again, if you missed a day, you can still, kind of get back on track. All right, so when we think about geometry then, right, it's all about shapes. And I would say the fundamental shape in game development is the triangle, okay? Without the triangle, we cannot possibly be successful. And the reason for this is because, first of all, we're working with addressable space. Think about the addressable space we're working with right now, right? It's 2D. But it could be extended to 3D, right? No problem. And what it allows us to do is build more complex shapes. Sometimes when we think about a triangle, we're thinking about it as pretty big. But triangles can get really, really tiny, right? And what that means is, because even if you look at something that looks spherical or circular, a lot of times that stuff that's been created is been created with triangles. In fact, you can estimate almost any shape with a triangle, okay, or a bunch of triangles. So triangles are our fundamentals. There's other fundamental shapes as well. You could think about a rectangle as something else as a fundamental shape, but really a rectangle is a couple of triangles, right, kind of put together. And that's really what they are. So whenever we look at something, we want to look at the components of a shape, whatever that shape is, in order for us to calculate how to complete the shape, the angles within the shape, and so on. Why do we care about these things in physics? Well, think about it. If I want to, use some kind of projectile that goes, from a point A to a point B, I need to know the angle of attack, right? How far it is up, the, how high up I'm going in terms of, a degree, how many degrees I'm looking up, as an example, where it's going to go down, how far it's going to go. That's usually the muzzle velocity. If I'm firing a gun, whether it's in a video game or whatever, there's some kind of initial velocity that I want to worry about, right? So the velocity is going to take me across a specific angle. And then we have to start worrying about other things we didn't talk about last semester, which is the big one, gravity, right? We live on Earth. If we were living on the moon, it'd be something different, or even on Mars. By the way, does anyone know what the gravity of Mars is? Off the top of your head, don't look it up. You might think it's like, pretty high, but actually it's like 0.34 Gs, which is really weird. I was like, wow, 0.34 Gs, it's like 1/3 of Earth's gravity. It means we'd like be titans on Mars, all of us, right, in terms of strength, until our strength went down and our muscles went away and we couldn't come back to Earth anymore. But the idea is that gravity is something that we're going to be using with triangles in order for us to calculate the trajectory we're going to be talking about of a particle that's moving over time. All right, so when it comes to triangles, we're talking about trigonometry. Right? We're measuring triangles. Triangles, and we're measuring them. That's what we're doing, trigonometry, at the end of the day. And trigonometry has some shortcuts, right, that allows us to calculate the triangle, the internal angles of the triangle, the perimeter of a triangle, all that kind of stuff. We'll be able to complete a triangle, after this today. We should be able to. When we think about angles, right, we're thinking about a direction, okay? And again, now think about this. This is fundamental stuff, guys, right? So if I'm thinking about vectors, then vectors have two components. What are two components that all vectors have? Yes? Okay, that's kind of like a point, but what else? For a vector itself. That's one of the things. Anyone else? Yes?
Direction and magnitude.
Direction and magnitude. So the angle is really the direction, and the magnitude is the length of the vector from the origin, from 0, 0. Wait, but that means that every vector is measured from the origin? The answer is yes. It really is, right? So if I have a point in space, you said x and y coordinates, if my x and y coordinates are 10, 20, it's 10, 20 from the origin. Okay. Let's talk about a little bit of drawing in 2D. Okay, where is my origin on many, not all, but many 2D addressable space systems? And I'm saying addressable space because it depends on the framework. Where is the origin? If I'm drawing something in 2D, right, where is that origin? Where is it? Yes? That's if we're drawing in 2D and I'm using Cartesian math and I'm doing it by hand. But where is it when I'm drawing with computers? Where is it? Yes?
Top left.
Top left corner. Which means that my y is flipped, right? My y is flipped. So when I go in, think about me drawing scan lines on an LCD or whatever. I'm drawing to the right, and I'm drawing down. That's what I'm doing. So I'm drawing to the right, going back, keep drawing to the right, going back, keep drawing to the right, keep doing this over and over again until I have all the different lines or rows of pixels on my screen. That's what I'm doing, right? So that's why it makes sense that the top left is the origin of when we draw, right? And when we think about that, if I said 10, 20, that's actually down from the top. It's not up like we would normally think of in math. This is a distinction we have to get used to, and a lot of times what we need to do is we need to flip our y-axis. So instead of a y being positive, meaning going up, y positive actually means going down. Okay, so this is just general things we need to know. All right. So again, we have two different directions, and what the angle does is it allows us to measure how much separation there is between the two different directions, if you think about it. And when we think about this, since we can measure this angle in any direction, right, we can look at this, kind of figuring out angles like this. By the way, I have to talk about this as well. When we're looking at things and we're looking to the right, usually that means clockwise, for those people that forgot. Guys, forgive me if you know this already. I'm just reviewing, okay? And if I'm going to the left when I'm measuring angles, I'm usually going counterclockwise, or if you're in the UK, anti-clockwise. That's a thing, right? Anti-clockwise to the left, clockwise to the right. So when I go clockwise, it means how the clock hands work. The clock goes to the right. Normally, that's how it goes. And when I take a look at this thing, if I go counterclockwise between A and B, in this figure, right, counterclockwise, that is my right angle. Right angles for us, my friends, are very fundamental, right? Right angles, it's really cool because what you can do a lot with right angles is you can figure out certain things. The right angle is what we can use all of our trigonomic equations with, okay, which is kind of interesting. So that's one thing to note. So a radius, we have to talk about radius and diameter very quickly. Radius is from the middle of the circle, if we're looking at this particular circle, to the edge, to one of the edges, one of the points around the circle. That's what a radius is. And diameter is from one side of the circle to the other. Okay, that's really what it is. That's diameter. So diameter and radius. And so diameter we know is 2 times the radius. And when we think about this, once we start thinking about this, and how circles work, right? Circles, again, are made of potentially a series of triangles. Here's your triangle right here, right? It's just that you have to connect the points on the circle here, because that's what you're doing here, right? So you have the center of the circle. You have a couple of points on the circle, A and B, that are marked. There's another point, C. And then what you're doing is you're trying to figure out the, kind of the angle in the circle. If I kind of connect all the angles in the circle, what's the total number of angles add up to? How many degrees? I know this is a silly question, but how many degrees? Yes? Hey, 360 degrees, right? Well, that means that if I go half a circle this way, or half a circle the other way, it's 180 degrees. If I go a quarter circle, it's 90 degrees, and so on. So when mathematicians started looking at this, they're saying, so degrees are okay. But do computers take degrees? Can I just plug in degrees on why? What do they take?
I think it's like
Radians. Okay, so one of the things that we're going to do in class and in your labs is convert from radians to degrees. Think about the word radians, right? Radii, right? How many, the radius, how many radians from the center to the edge? How many of those exist in a circle? Pi radians, right? If I look at the pi, which is a kind of a magic number in our our universe, if you will. It's a magic number because pi is non-terminating, non-repeating. Okay, who can spout off pi to me in at least 10 digits? Anybody? 10 digits. Go.
3.1415926535.
You're awesome. Yeah, that's good. You should at least know 3.14. Okay? If you don't know pi is 3.14, then by hand you can't do any of this stuff. And you should know, how to use pi to hand calculate a circle or any other kind of angle that you want in the future. Do I expect this from you this semester? No, I think it's good to know. Okay? If you use degrees and you can convert with some kind of formula from degrees to radians, you're good to go. One thing to note though is how many pi's do we have in a circle? Does anyone know? Yep. 2 pi? Okay. So what does a pi mean? If I say 1 pi, what is that? Right, but what does that mean in terms of angle? 180 degrees. Isn't that wonderful? 180 degrees. That means if I go from here to here, it's 0.5 pi, right? Now, again, you might say, I'm bored, Tom. Why are we talking about pi? Right? Because it's going to come up. I'm going to ask you if you have pi radians, right? Or 2 pi. If I say 2 pi or 3/4 pi, you should know what that means. It means, take 90 degrees, right, as an example. If I say pi, it's 180 degrees. Half a pi is 90 degrees, and you should be able to go from there. Okay, so that is when we talk about angles. There's different kinds of angles that we're going to be talking about as well. There's acute angles, and there's also obtuse angles. And you can see that all the angles, like we talked about, add up to 360 degrees. So what ends up happening as well is they're measured in arcs, if you will, right, from one position to the next. And one of the most important angles we talked about was the right angle. And a lot of times we say that things are perpendicular, right? Or in translation for us, programming language, at right angles to, right? That's what perpendicular means. At right angles to. So if I say something like, my hand is perpendicular, to the floor, right? As an example, it's at right angles to, what's the right angle from my hand to the floor? That's what I'm saying, perpendicular. Okay. There's also parallel, which means things are running in the same direction. Okay. Perpendicular usually means that I'm creating some kind of 90-degree angle. And one thing we also talk about is quadrants. When I first was learning quadrants again and reviewing quadrants, I was thinking, I'm a Star Trek guy, so I'm thinking of the delta quadrant. But each of these quadrants, really, at the end of the day, when you think about this, is denoted by x and y coordinates, right? And in math, this would be positive x, positive y. But not so in computers. This would be positive x, negative y, because we're going up the screen, correct? Okay, so please keep that in mind, that in math this looks like this, but we need to flip the y a lot of times. So this positive area right here would have a negative y component when we're drawing, okay? And so each of these things, this is incorrect as well then, right? Because it's negative x on this y. The x is the same, but the y would be a positive y because we're going downwards, right? Anything on the downside, just kind of multiply y by -1, and that's what it would be. Okay, so keep that in mind when we look at this kind of thing, because when we talk about quadrants, and I say the positive quadrant, you should know what it means. The positive quadrant would be the top right corner. Okay. And so we talked about acute angles, so again, smaller than 90 degrees, and obtuse angles are then larger than 90 degrees. We're just talking about naming. We're just labeling stuff for you guys to know. So when I say it's an acute angle, you know what it means, okay? And so anything that's greater than half the circle is called reflex angles, but we're not going to really talk too much about those, okay? So once we have radius, then we can talk about pi. We talked about that. If I want to find the area of a circle, it's really way down here. It's pi r squared. It's a famous equation. You guys should know about this as well. And the area means all the space that's inside of the circle, okay? Very, very simple. And guys, I got to talk about this for a second and interrupt myself just one more time as an aside. If you're bored, and if you know this stuff, wonderful. But I want to warn you that this course scales, which means that you start off and we're talking about angles and we're talking about vectors, and then we're talking about, you know, something crazy like calculate the trajectory of, you know, of this, whatever it is. I'm throwing a grenade, and I want to make sure that the grenade hits properly 2,000 meters away. What's the angle that I got to throw the grenade? How much is, you know, you can keep going from this. Physics is very, very, you know, kind of broad. So please, I'm slowing it down here so you understand that this is like the fundamental stuff that we have to talk about, okay? Any questions before we go on? All right, let's move on. So again, when we talk about circumference then, we talked about pi's, so circumference, the area, you know, if I walk around the circle, that's what circumference means, right? It's 2 pi r, okay? We talked about radians, and again, radians is, you know, kind of a way that computers understand angles, and we need to convert between radians and degrees, like I said before. Okay, so, and I talk here about how to convert it in the PowerPoint slides, and again, there's very simple ways. One thing to note is this. People have asked me, you know, so should I remember this stuff? You know, Google it. It's okay to Google, guys. Googling is a good thing. We all do it, right? Look it up. And one of the things that you're going to notice in the engine that we've given you is in our, if I'm not wrong, the util library, we have a, you know, kind of rad to deg calculation. You can just multiply rad to deg by radians and get degrees, and there's also deg to rad. It's actually a, you know, kind of a variable that you can multiply by, and then you'll get the conversion. You don't have to do this by yourself. And we frequently go back and forth because sometimes I want to display degrees, but I want my, you know, the program to calculate it in radians. All right, so we're going to go back and forth on a regular basis. Let's get back to talking about triangles. Okay, so again, it's extensively in geometry, any kind of geometry you want to use. It's, again, when we think about a triangle, what is it? 3 points in addressable space. That's what it is, right? And one thing to note is that these points are non-collinear. What does that mean? What does non-collinear mean? Non-collinear. Well, it kind of says what it is right here, right? But what is non-collinear? What is linear? What is linear? If I was going to say linear, what is it? Yeah. Straight on a line. So imagine if I had 3 points in the same line. Is that a triangle? 3 points, right? It can't be. That's why it says there are 3 non-collinear points. They can't be on the same line, right? If I have 2 collinear points on the same line and another one up, above, or below, you got a triangle, right? But we can't have all 3 on the same line. That's what it means. That's kind of a, if I was going to make a computer program to say, is this a triangle, to calculate to see if the 3 points are a triangle, that's what I would check. Are they all 3 collinear? If they are, it's not a triangle. It's a line segment. Okay, each point of the triangle is referred to as a vertex, and to get together they make the vertices of the triangle. Okay, so triangles, again, there's 4 main types according to the 3 triangles inside them, right? And as illustrated here in the figure, right, we have this triangle, and a lot of times what we do, guys, when we look at triangles, is we use you know, capital letters like A, B, C to denote the vertices A, B, C. Again, these would be x and y coordinates, right? Vectors in 3-dimensional space or 2-dimensional space. We use Greek letters. I'm a Greek guy, so I understand Greek letters. And you might be like, why do we use Greek letters? We don't need Greek letters. We can use some other Greek letters. Because that's how it is. It's, you know, that's what math does. They use alpha, beta, and gamma, right, for the angles inside. A lot of times, though, you'll see that the angle is theta. The general angle is what that is. If I use theta as an angle, it's the general angle. If I'm using multiple angles inside of a triangle, I'm going to use probably alpha, beta, gamma, or something else. Okay? There's also these edges. Sometimes they're also called the legs of a triangle, right? And these edges that go from one vertex to another they're also labeled, right? And they're usually labeled with small letters A, B, C, as an example. And when I first looked at this, I was like, how did they come up with like the naming scheme? Like, how come A is here and B is here and C is here? How come? I don't know. Yeah. They're opposite of the vertex. Very good. So I want you to think about line of sight for a second, right? So C, let's suppose, is the shooter, and capital C, and lowercase c is what the shooter can see, right? Line of sight. That's how I can look at it. It's almost like when I'm at a vertex, I'm seeing the edge, the opposite edge. Opposite edge. One thing we're also going to know is opposite and adjacent, right? We're going to talk about opposite and adjacent. We're also going to be talking about something called a hypotenuse in a second. So this is the opposite edge, but these two edges, this one and this one for now, because this doesn't look like a right angle triangle. These are both adjacent edges, all right? So we have adjacent edges and we have opposite edges. The opposite edge is it's the lowercase letter related to the vertex. Why do we care about this stuff? Is it important for programmers? Well, yeah, if you're labeling something and if you're trying to figure out, how to draw a triangle in OpenGL or in DirectX, it's important to understand stuff. We can combine triangles, like we said before, and to make a more complex shape. Here's an example of a more complex shape that we can make, right? And remember that the internal, okay, here's something else. What do the internal angles of a triangle add up to? 180 degrees, right? Which is in pi? Pi, right? So we have pi radians inside of a triangle. And one really interesting, I would say, feature of triangles is they repeat in terms of angles inside. The internal angles, you can see, are repeated. So this angle here, right, at the top right corner, right, is the same as this angle in here, is the same as this angle in here, and so on, right? You're going to see that repetition. If A, alpha, beta, and gamma make up 180 degrees, and if these angles here, the internal angles, are also alpha, beta, and gamma, right, if that's true, well then, so too is this, alpha, beta, and gamma, right? It makes up this 180 degrees right here. You can see how that works. So it's kind of interesting. And there's a lot of symmetry. That's why when we start talking about triangles and so on, I think about them as building blocks. I think about them as foundational pieces when I start, creating shapes. Okay, let's talk about some types of triangles. There's almost like categories of triangles. If I was going to think about a character loadout for triangles, right? Like the warrior, the priest, the wizard, right? Those kind of things for triangles. I think about the same things for these ones. There's a loadout for each of the triangles that we're looking at here, right? So the first loadout is an equilateral triangle, right? Simplest triangle, right? Which is all three equal sides. Something like this. Let's say if there was something like, let's suppose that this one is equilateral. Actually, this one here. Because you can see that the sides are all marked with this, they're all crossed singly. And that means each side, that denotes each side is the exact same. An isosceles triangle, that's the second loadout, is one that has only two sides the same, right? And this one has all three sides different in terms of length, right? So why do we care about this stuff, right? Scaling triangle. The reason for this is because, well, if this is an equilateral triangle, then what are the angles inside? What are the angles inside? Sorry for the mic. 60, someone said 60. Yeah, because they're all equal length. If they're all equal length, then the angles inside are also equal. In many ways, this is a magic triangle of some way, in some ways, right? Because if each side is the same length, then all the angles inside are also 60. What are the angles here, potentially? Do we know what the angles would be here for an isosceles triangle? Is there a special angle? No, because there's a lot of different angles we can use. We can have a very acute angle, much more acute angle with the same length, if you really want to, much longer sides. So this is not so known, but that one we do know. This one, of course, we don't know anything about. Okay. So again, three loadouts, right? Equilateral, isosceles, and scalene. And it means just in terms of the way that triangles have been created. The right angle triangle, like we talked about before, is very special, and it has additional things other than just the sides or the legs, if you will. It has something called a hypotenuse. Let's talk about this right angle triangle very quickly. So again, here's alpha and beta, right? And if we know, usually there's a little square at the bottom of the right angle triangle. If we know that the square of the right angle triangle means it's right angle, it means that that's 90 degrees. Then we know that the sum of the other two angles must also be 90 degrees. Okay? Now they can be other numbers. It doesn't have to be exactly 45 as an example, right? But they're going to have to add up to 90 degrees. And the other thing is that notice that the C, so I'm going to walk over here, so for the people who are phasing out over here, and you're losing your concentration, so hopefully you'll follow me around the room in this great stage. In the C, if you look at the C, the capital C, which is the vertex in the bottom left corner, right, then the hypotenuse happens to be across from that. So there is no lower C, like lowercase c anymore, right? It's the hypotenuse when we're looking at this triangle. The rest is the same, but hypotenuse means it's the opposite leg from the right angle. That's what it means. That's what that hypotenuse is. Okay? Again, this would be another loadout, and this is a special triangle. We always want to get our triangles into this configuration, because if we can get our triangles into this configuration, it's much easier for us to calculate the other two sides, right? Or the other two angles. It's totally easy to do that. If we have an isosceles triangle, it's more difficult to calculate. Equilateral obviously is the easiest, but this is pretty good a lot of times in terms of calculating or we like to say is compute the triangle or complete the triangle. When I say to you complete the triangle, it means I want to know everything about the triangle. I want to know its angles internally. I want to know the length of its edges. I want to know, all of its vertices, all that kind of stuff. Okay, and once I know those things, I'm well on my way to using it as a building block. Pythagoras, oh yes, my friend Pythagoras, my Greek guy, right? He really developed different theorems relating to right angle triangles, and then those theorems, the Pythagorean Theorem, was developed. So what is the Pythagorean Theorem? This is from, before we go on to the next slide. What is the Pythagorean Theorem and why do we need it? Yes?
A squared plus B squared equals C squared, and it's how to find the
Okay, A squared plus B squared is equal to C squared. And if I wanted to find C, what do I do? A squared plus B squared is equal to C squared. So what you found? You found a relationship between, the edges of a triangle, right? So you did. You said, okay, I want to find the length of something. The length of the hypotenuse is the square root of the squares of the two sides. That's what he's talking about. So we use square root a lot of times when we want to find the distance. Let's go back to that right angle triangle for a second, right? I want to find the distance. I want to find the distance between, A from A to B, right? I'm going to use a right angle triangle. I'm going to use Pythagorean Theorem to figure out the distance. And most likely, I'm going to need to use square root. Is square root is good to use every frame? Can I square root everything? What do you think? You're shaking your head. What is it? Why is it bad?
I think it's a really computational heavy.
I love your words. It's computationally heavy, is what you said, right? Let's talk about it being computationally expensive to do square root calculations every frame. One frame is, a lot of times, 60 times a second. We have 60 frames in 1 second, maybe more nowadays with video games, 90, 120, whatever. So imagine I'm doing square root calculations, a bunch of times every second. It's computationally expensive. We don't want that to happen. So what is an alternative to finding the distance or doing distance calculations instead of using square root? What do? There is a solution, believe it or not. We did it last semester.
Sine.
What else? What else can we do? Square distance. We can use the square distance. We don't. Yeah, you guys already knew what it was. And the reason why we use squared distance instead of square root every frame is because it's just a number, right? Why do I need to use distance calculations? Collision detection, collision response. The distance, I'm trying to calculate the distance. Do I have line of sight? I can go on and on. We use distance calculations for so many things in game dev. And that's why Pythagorean Theorem, the father of game dev might be Pythagoras, if you think about it, right? Because he was the one that was able to calculate distances. If I know the distance between me and you, and if I know that I'm coming closer to you, pre-COVID, right? And if I bump into you, right, as I said, if I'm close enough to you within your comfort zone, then I'm hitting you, right? And if I can do that calculation every frame, I have collision detection. The simplest collision detection we're going to be talking about in the second half of the semester is circle, circle collision detection, where I do an overlap between two circles. The distance, using Pythagorean Theorem, between the two centers, right? And the difference of the radii. If the radii, the combined radii, the distance between the two centers of the two circles are less than the combined radii, they're overlapping, right? I've got an overlap, which means I've got a collision. That's how it works. So distance is huge, and Pythagorean Theorem is important, but we also need to know when to use it and when not to use it. And we don't want to use Pythagorean Theorem and distance calculations with a square root sign every frame. We don't want to do that. Okay, so why right angle triangles? So think about this now, right? If I take a regular triangle and I split the triangle in half, I'm going to have two right angle triangles. Here's a regular triangle, I split it in half, I got two right angle triangles. If I have right angle triangles, I know that there's got to be a 90-degree angle somewhere, which means the other two angles over here and over here are easier for me to calculate. Okay, so that's the one thing we start doing. We start splitting triangles, more and more in order for us to be able to calculate them easier and to complete them easier. So again, they were calculated. Here's that equation, right? Kieran was just talking about that equation. C squared is equal to A squared plus B squared, right? And there's the completed equation with the square root sign. Okay? And one thing to note is I want to talk about magic triangles, or what we like to call triples. This is an interesting thing as well. By the way, guys, this is super important to understand and to make it so that you're able to quickly calculate stuff when it comes to, if you're going to hand calculate anything in computer science. Magic triangles, if you will, or triples, they have special properties. If I have 3 and 4 here, I know that this length is going to be 5. We call this a 3, 4, 5 triangle. It's a magic triangle. And they exist naturally in the world, all right? There's a lot of these triples. Here are some of the other ones. Pythagorean triples or magic triangles, what we call them. 3, 4, 5, 5, 12, 13, and a bunch of other ones, okay? The other one that I like to use is 1, 1, root 2. That's a very, kind of common triangle, right? So do I need you to know all of these? No, but you definitely should know 3, 4, 5. I mean, that's like a silly one not to know, right? 3, 4, 5 triangle. Why? Because once I have a 3, 4, 5 triangle, and if I understand what a 3, 4, 5 triangle is, I can quickly calculate the angles, and I can quickly calculate the sides, which is what we want to do. And why? It saves us time. That's really what it is, time savers. So Pythagorean triples are really, really important, and I recommend you don't lose track of them. So here's some common ones that we talked about. A 1, 1, root 2. 1, 1, root 2 triangles have 45 degrees, right? By the way, they're all right angles. Okay, they're not like funky different triangles. A 1, 2, root 3. 1, 2, 3, instead of 1, 2, 3, 1, 2, root 3. If you remember that one, then you know that there's 60, 30, and 90 degrees. A very nice, a very nice triangle. 45 degrees. There's a special thing, a special feature, if you will, or property of 45 degrees. Okay? Here's something that I want you to remember. We're going to talk about it again when we talk about projectile motion. At 45 degrees, firing a bullet at 45 degrees at whatever velocity you want, I'm going to get it to the maximum distance, always. So if I actually take a gun or some kind of arrow, bow and arrow, kind of angle 45 degrees from the, from the ground, I kind of shoot it up, it's going to go the farthest it can possibly go. Why? Why do you think that is? Again, I'm just talking about this with you guys just for interest. It's because of gravity. That's how gravity works. 45 degrees is a magic number for how far we can shoot something. I'm going to ask you about this again. Take note. Might even be on the little quiz we might do one day. All right, so 45 degrees is very special. 30 and 60 degrees also are interesting angles because at 30 degrees and 60 degrees, we use those a lot for firing arcs, actually. If I make a war game, whether it's some kind of a real-time strategy game or whatever, I'm going to have a firing arc, right, in front of my gun mount or whatever it's going to be. A lot of times I use 30 and 60 degrees as the common angle, or 90 degrees. 30, 60, 90 is very, very common. So that's why 1, 1, root 2, and 1, 2, root 3, and 3, 4, 5 triangles are things that if you're going to memorize any triples, Pythagorean triples, it's going to be these. It's going to help you a lot when it comes to in your mind, you're like, oh, it's got to be 30 degrees. And people are going to go, how does he know? How does she know? How do they know that there's like, that this thing, you know the Pythagorean triples? Okay. So a lot of times what we want to talk about is another feature, if you will, or property of trigonometry is something called the gradient or slope. A lot of times we want to get the slope of a line. We're moving away slowly from triangles. We're using triangles as a fundamental, and we're going to be using triangles to calculate other things. So if I have this graph, which again, if you notice, on the y-axis and the x-axis, right, you can see that here we're talking about math. This is not, we're not talking about drawing in 2 dimensions. But you can see here that there is a right angle that you can draw, right? And you can figure out the slope of a line, this line segment from the origin to xy, right? And you can find out what the slope is. The slope, really, if you think about it, is has a bunch of components, right? We can say that it's, a lot of times we want to say it's rise over run. You might have heard that in high school, or even earlier, hopefully. And, or A over B. Okay, really big point to talk about. If we ever talk about sine and cosine, in general, whenever I want to find the slope of anything or I want to find the angle of something, right, it's usually sine is associated with the y-axis a lot of times, and cosine, very many times, is associated with the x-axis. So that means if I take sine over cosine, we're going to see those things coming up again, right? We can try and use those two things to figure out the distances. One thing to note also is, so why would I use sine and cosine? I can componentize, I can get the components of a line by using sine and cosine. Okay. Remember we talked about magnitude? Vectors are magnitude and direction, right? Here's where it gets a little bit more complex. I'm shooting a gun, or a cannon. Let's use a cannon, not a gun. Okay, but we live in Canada. So we're shooting a cannon, at a specific angle, right? Some elevation. Elevation means from the ground plane, right? I'm shooting some kind of cannon, and I want to find the components, the x and y components, of that, kind of angle, right? Or that line segment. How do I do it, right? I can take the magnitude, right, which is my muzzle velocity. That's really my magnitude, if you think about it. The muzzle velocity, how fast that bullet or projectile is coming out of the muzzle of a gun or a cannon. That's the magnitude of your vector. I'm going to multiply it by cos theta, right, to get the x-axis. We're going to get, and I'm just giving you a preview here, and I'm going to multiply by sine theta to get the y-axis. And what is theta? This angle right here, the angle that's closest to the origin. If I take those angles, if you think about what I just did, I can deconstruct, right, my line segment into a right angle triangle. Okay? And that's why right angles are really important, and that's why triangles are super important, because we can start calculating things like this. Okay. Questions so far before we move on? I know that this is like, dry stuff. and I'm talking about things on the screen, and we're not actually doing something together with programming, you're just watching, it's like a show, right? And people, you're probably going to get more out of watching Netflix or the latest House of Dragons or whatever you're going to watch than watching me, right? So the answer is, don't be bored, this is fundamentals, right? And you need to know these things because if we're going to, like I said, this scales, this ramps pretty quickly, right? And it's already done that without you knowing it, believe it or not, because I'm already starting to talk about rise over run. I'm starting to talk about how to calculate or deconstruct a the components of a line segment. And once I start going there, we have a lot of other building blocks that we can use to do other things, like we can create motion graphs. We can do a lot of stuff with things that we've got already, believe it or not. Okay, so we talked about a lot of things here. One thing that we talk about here is this sine and cosine. And sine and cosine, for yourself, when we start thinking about what sine and cosine is, a sine wave, right, represents kind of like peaks and valleys, right? A sine wave. Where does a sine wave start? If I was going to draw a sine wave from the very beginning, by the way, does anyone not know what a sine wave is? Hopefully you guys all know. Sine wave, where does it start? Does it start at the origin? Where does it start? Some people say yes, some people say no. At the origin? At the middle? And what happens is it goes up. How many pies does it go up? The sine wave. If I go up to the top of the sine wave. So I'm coming from the bottom, from the origin, I'm moving up. How much pi, in terms of pi, I'm moving up? 0.5. So I'm moving 0.5 pi up to the peak. I'm going 0.5 down, so it crosses the x-axis again. Then I go 0.5 down, so it's below the x-axis, and 0.5 up again, so it meets the x-axis. Guys, we've just been able to draw a sine wave. If I can draw a sine wave, I can calculate sine with no calculator, right? At least for basic values. For example, what is the sine of 90 degrees? You should have it right now. Think about it. Is it? Right, because it's up here, right? And what is the sine of 180 degrees? 0, right? The sine of 0 is 0. The sine of 180 is 0. The sine of 90 is 1. And the sine of, if I go back down over here, the sine of 270 is -1, right? And so on. And that's the way you can get those things, right? So once we have that, I can draw that thing. Okay, how about cosine? Cosine is like sine, but what's the difference between sine and cosine? If I was going to draw cosine, how do I draw it? What's the difference? Anyone know? Cosine doesn't start at the origin. Cosine starts 1 up on the y-axis. So it's kind of offset a little bit from the origin. So if cosine starts at the top, and if I say 90 degrees in cosine, what is 90 degrees? Cosine is 90. 0, because it goes from here down like this, hits the x-axis. Again, we're going to visualize this in a second, but I want to talk about it with you because you should be able to quickly calculate these little parts of sine and cosine. When we combine sine and cosine, right, as an example, and sine over cosine, we get something called tangent. Tangent is super important because then we can start talking about something that is tangent or at 90 degrees to the origin. If I'm tangential, we're going to hear about these words, tangent and tangential. That means that I am at a 90-degree angle outside of a circle, right? At 90 degrees or at right angles to a circle. I'm tangent to it. I'm tangential, right? Which is kind of interesting. So that's sine over cosine. Again, don't panic. We're going to get back to this. I'm just previewing, if you will. All right. So we got tan, cos, and sine. Everything takes radians, like we said. And one of the things that you should, we can think about, and back in the day, when we started this course, we had a bunch of quizzes and questions all around, trig, right? And Pythagoras and later on other mathematicians sat down and they said, there are some relationships that we found, right? One thing for you guys as programmers that I always want you to think about is, and I'm going to say this a lot of times to you, is make it work, then refactor. I'm always going to tell you that stuff about programming, right? I'm never going to say to you, do right the first time. That's for house making. If you and I are building a house, do it right the first time, right? Because if we don't do it right the first time, house is going to fall down, right? For us, that's not us. That's not a reality for us as programmers. For now, I want you to make it work, guys. Whatever that program that you're making it work is. Then we're going to refactor and make it better. That's what this is. This is refactoring. Mathematicians started off with the basics, sine and cosine, and said, hey, you know what? Look, we found some ability for us to refactor things to make it easier for us to solve equations, to solve a triangle. That's what this is, right? That's what these identities are. So, you know, we're going to see some of these, and I want you to use these almost as a cheat sheet sometimes when it comes to, you know, to kind of figure out the angles, the internal angles of the triangle if you need to, if you get down that road. Okay, so trig identities, I'm showing them to you. I don't expect you to memorize them, but they're quick refactorings for us to quickly figure out some relationships, right? As an example, without us doing the hard work or heavy lifting. That's what it is. And here's something we can do. If I have numbers from 1 to 12, here's an example, and I'm dividing by a number between 1 and 12, and then multiplying it by 3, right, as an example. Dividing by 12, multiplying by 3. What if I just divide by 4? Isn't that a refactoring in some ways? Think about it, right? Divide by 12, right? Multiply by 3 or whatever. I mean, it's kind of like, that's the kind of stuff that we end up finding. And the reason why I'm bringing this up to you, and it's just a silly example, is because this is what we do as programmers. We're sitting there saying, how can I make this simple? One thing you can also get from us in this semester is you're going to see a series of kinematic equations, right? To make it more realistic-based physics. But guys, remember, we're always trying to make it so that it looks good enough. Right? This isn't about making a simulation. You're guys are making games. Do I care if the thing is perfectly like, you know, how it's going to go like it would be? A lot of times, let me tell you right now, I don't use 9.8 meters per second, which is gravity, right? When I do video games, any platformers or whatever, no, I use like 30 meters per second or something like that. Why? Because it's more snappy, right? It looks better when the thing falls faster, right? Because it feels floaty when someone is jumping at 9.8 meters per second with gravity like that. So you're going to see that we're going to make modifications to some of these things as we go. Okay. We talked about inverse functions. There's arcsine, arccos, and arctan. Arctan is really important. That's the one I use the most because then I can calculate the angle, right? If I have sine and cosine, right, as the angle, sine over cosine, I can calculate using arctangent, and actually A tan2 is what you can use on your computer to calculate the angle of attack by having the components of the triangle. We're going to see that a lot. This is a very important rule, the sine and cosine rule. This is the sine rule, and the sine rule basically defines the relationship. Way back, remember we saw a bunch of slides ago, we saw a bunch of angles, alpha, beta, gamma, right, at the corners. And then we saw little a, little b, little c. That's the opposite side. So what this is a relationship between the angle and the opposite side, right? That's what it is, the opposite leg, if you will. Right? And what we're saying is there's a ratio that we can figure out. If we know a lot of this information, we can figure out this information. That's what we're saying, right? So that's what it is, and it's very, very important to know that. But also important to know is that the sine rule only works for right-angled triangles. Okay, it does not work for other non-right-angled triangles, and that's where we use the cosine rule. Okay, so it's more complicated. Right, and it's an extension of Pythagorean Theorem. It's like I'm saying a squared is equal to b squared plus c squared plus 2 minus 2bc cos alpha. Right, you just add that in, and you can use the cosine rule to find things when it's not exactly a right angle. Again, I'm reviewing this with you, and I'm flashing these things, you know, kind of up, and you're gonna be like, okay, I don't know what that means. I'm not really applying it right now, but I'm talking about this just to hopefully trigger some memories from high school, if you did high school trig. Anyone not do high school trig? Yeah. So for those people who didn't, and it's brave that you said no, but if you didn't do high school trig, then this is all new to you, and that's okay, right? How about anyone not do high school functions? You guys should all know functions. I'd be very surprised if you didn't. And if you didn't by now, you know what functions are. All right. So a lot of times what we want to do is find the area of a triangle. That's also a, kind of an exercise that we want to, kind of follow up with. I want to find the area of a triangle. And we know some measurements, right? But one thing is, the general area of a triangle is half base times its height. Okay, half base times its height. Well, if I know what the base is, so here's the base, right? And if here's the height of the triangle from the top of the vertex, it's vertex B, all the way down to this point P, right? That's how I can calculate the area of the triangle, half base times its height, right? Which is pretty simple. Okay, I know it's really not exactly the most exciting stuff. Oh yeah, this one, Sohcahtoa. Sohcahtoa is what I always remember it as, right? Sohcahtoa, right? The reason why I remember Sohcahtoa is because it allows us to find, to use relationships to find, different parts of a triangle given certain pieces of information. Okay, so a good example of this is if I have opposite and hypotenuse, and I'm looking for the angle x, then I can say that sine is equal to opposite over hypotenuse. I can use the sine of x, and I can get this relationship. So I can use the two things that I know to find the third thing. Okay, that's how we use Sohcahtoa. Sohcahtoa or Sohcahtoa, however you want to remember it, is a way of completing or solving the triangle. That's what we want to say. I want to solve the triangle. How do I solve it? I have tools that I can use to do it. And this is some quick tools. These are some quick tools we can use. Okay. Sohcahtoa. So here's some examples. One thing to note is I'm just going to pull up a tool that we can use a lot. And for your first assignment, a lot of times I ask you guys to use different tool. One of them is called Desmos. Let's pull that up with your laptop for a second, if you don't mind. So if I go to desmos.com, right? Desmos.com has a lot of really cool tools that are built into it. Math tools is what it is, right? And what it also does is provide us with a graph if we want to, calculate stuff, right? The great thing about Desmos is you can do a lot with it. Like for example, if I wanted to put an equation of a line, I can put it in here just like I would normally do. So for example, if I said the equation of a line is x, that means y is equal to x. That's a linear equation, right? One thing you can do is you can drag it around. You guys should have seen this before. And Joss is going to go over line segments and how to create triangles and so on with you here with Desmos as well. As we zoom in with Desmos, you can see that there's a lot more detail, right? A lot more detail. They can really zoom in. Okay, so really great little tool, and for free, of course, too, which is really awesome. Free is always good. What you want to do with Desmos is if I wanted to have an equation of a line, I could do something like, well, I know that x squared is something like this, right? How did I do that? X, little caret, 2, right, is x squared. And notice what it does for us. It gives us this parabola. That's what this parabola is, right? And it's kind of like this curve. So instead of, we can also say that this is a curve, right? What we saw before, this is a curve too. If I said just x, that's a curve. It's just the linear curve that we're talking about here. So why are we talking about curves? Because I can use triangles. I can use triangles to figure out the point on a curve, can't I? Right? If this is a linear, kind of curve here, right? Then I can figure out from here to here to here. I can use Pythagorean Theorem to find the distance between here and this point right here, okay? The great thing also about using Desmos in general is that you can do other things, other calculations, like for example, sine of x, right? And then you can have your little sine wave, like we talked about before. So this is exactly what we said. We said that sine and the properties of sine, let me just bring this closer in. The properties of sine start off where sine starts at the origin and moves up and then comes down and then goes and repeats, right? That's kind of what sine looks like. Whereas if I change this to cosine, just to demonstrate this again, a cos of x, cosine is offset. You can see that cosine starts up here and then works down this way. Okay, so that's the difference between sine and cosine. Again, you should be able to calculate these things. And what Desmos does is it gives you all those values, okay, for you immediately. A lot of times you want to use graphing calculators like this one instead of us graphing it by hand. So if we have this, then let's go back to that question that we have in the PowerPoint slide. The PowerPoint slides are giving you some questions for you to practice, right? Understanding things like equations. One thing that we're also covering today are things like algebra. What do I do here? If I want to plot the points here, how do I plot the points for x squared plus 4x minus 4? How do I do that manually? I want to draw this, right? And I don't want to use Desmos. I want to confirm it with Desmos, right? How do I draw this manually? What do I do? Anyone? What's a strategy that you can use here to break down this equation of a line or a curve? Anyone know? Algebra is something that we're going to be covering extensively this semester, right? And it's expected of you to know how to factor, right? And a bunch of other stuff with algebra. If you forgot algebra, right? So how do I do this? If I was going to try and draw this out, there you go. I can make a little table, right? And the little table that I want to make is I want to plug in values of x, right? To start thinking about how do I get y? F of x, if you look at this equation here, that's how we kind of talk about this. If I say f and then this function of x, f of x we call it, right? In my mind is like y. That's y. Okay? If I pass an x to y, I make a relationship between x and y. I'm passing x as a parameter to the function to give me y. That's what f of x is, right? Imagine that x is my parameter, and the function that I'm passing into is going to return y, values of y. That's what it's going to do, okay? If we know this, then if I plug in different values of x, random values even, right, we're going to get that curve, right? So example, if I plug in 0, when x is 0, then y is? Minus 4, right? When x is 1, if I sub in 1 in there, 1 squared is 1, plus 4 times 1. 1 plus 4 is 5, minus 4 is 1. So when x is 1, y is 1. Let's confirm it with Desmos. So if I plug in this value, and this is something we're going to do on a regular basis, let's see if I can do it with one hand. So here's x squared. So again, it's you write it like this, caret squared, right? You use your arrow keys to kind of move over, right? And then you go plus x squared, I think it's plus 4x, right? And then minus 4. There it is. That's the line we're talking about here. This is the line that we've defined with this equation. Let's make sure it's the same equation, right? And if we look at it, if I plug in value of x, that's 1. So when x is 1, that's right here. Let's zoom in. Then y is 1. And if I hover over there, you can see that that's true. When x is 1, y is 1. When x is 0, then y is minus 4. Okay? When x is 0 means it's on the origin. Then y is minus 4. That's where it intercepts from y. That's the y-intercept, if you will. Okay? Okay, so that is kind of how equations work out. If I was going to draw something, I get a table of values, and I plug it into the equation. That's what I'm doing. I'm plugging a table of values, random values even, into equation, and we get a nice representation of the line. Okay? Example 2. So, how do we plot this one? We can do the same thing. Let's see if you can do it in your head. If I was going to plot this out, it's very similar, but when you look at this equation compared to this one, this was a straight line. What kind of line would this make? Is this still a straight line? What are your thoughts? Yes? Is it a yes or no? Is it a parabola? Okay. Let's talk about why. Let's talk about why. So if I plug this equation into Desmos, if I plug in 0, let's start with 0. So if I go where x is 0, y is 5, right? When x is 1, now it gets a little bit more complex. 1 plus 3 is 4. 4 squared is, guys, 4 squared is 6, thank you. Minus 2 times minus 2 is minus 32. Minus 32 plus 5 is, thank you, right? And that's how it goes. So you can see that was a wildly different value for 1 point, a 1 point difference from 0 to 1. That in your mind is sometimes a good indicator that it might not just be a linear equation, right? And let's try this out. If we're going to copy this in Desmos and see if we can do that. So again, if I go into Desmos, you can do this yourself. And if we just use another line here, we can have multiple curves here. So again, let's see what this looks like. Minus 2, right? And one thing to note is if I use brackets in Desmos, right? So x plus 3, is that what it was? Squared, all squared. So all squared means like this, all squared, right? And then plus 5. So I'm going back and forth because I don't remember. And then if I was to do that, so that's what it looks like. Where is that equation? Where is that line? Well, it looks like this. And actually, we were kind of fooled because if you think about this was also, it looked like a straight line where we were looking. And that's why I wanted to show you this, that they're both curves, right? Both of them are parabolas, right? It's just we were focusing on this part. When you look at something like this is why a table of values, right? Although it's helpful for us, what ends up happening is it might look like a straight line in one section, but what happens is also it becomes something like this different. Yes?
So if we were to put the stuff into the programs, it would be flipped, right?
Correct. Yeah. Because this is drawing, you're drawing in for Cartesian math, right? This is a Cartesian curve, right? For putting it in to draw it, if I had a drawing program that plotted points, yeah, so then you'd have to flip the y, is what you'd have to do. So it would be flipped over the x-axis. That's what it would be, okay? But very good observation. So if you look at this, they're both curves, actually. And the first one, there's a parabola that kind of goes beneath the x-axis, right? And the other one is a parabola that goes above the x-axis. Here's an interesting feature of this, all right? There's 3 parts to this, okay? When I look at a general equation for a line, what's the general equation for a line? Does anyone remember? General equation for a line. Yes, in the back. Y is equal to mx plus b. And what about if I want to find the general equation, the quadratic equation? What's the quadratic equation? Excellent. Ax squared plus bx plus c. Ax squared plus bx plus c. Where we have the coefficient a, b, or c, right? Multiplied by the factor, whatever that is, right? So here's something. What if, let's just use this equation first, okay, the first one. So here's the red line. This is the red equation. What if I take this equation and I change the 4? What if I flip that value of 4? What's going to happen to that line? What do you think is going to happen? What does this minus 4 do? This is ax squared plus bx plus c. Moving up and down, let's see if that's true. So if I take the 4 away, right, then what happens is it moved up, right? If I add 4 instead of subtract 4, right, then you can see that it's just going to move up and down. That's what this last term means. By the way, when we're looking at these equations, we have 3 terms is what we're talking about. The first term, the middle term, and the last term. The first term is x squared, right? The middle term is 4x, and the last term is just a literal 4, right? Ax squared plus bx plus c. Okay, so what happens if I change this value, the middle term? What happens to this equation again? What does this do? So we know that the 4 does this. What does this do? Go ahead, you were just saying left and right. Okay, so if I do a minus 4, or a negative 4 here, so instead of a positive 4, I do a negative 4, then a negative 4 seems to move it to the right, right? And if I add 4, so positive 4, it moves it to the left. So it's actually inverted. So this middle term, the middle term, if I change the direction, right, or the sign of the second term itself, it moves the whole curve to the right and left, right? And the last term moves it up and down. With those two things, you can start calculating. If I wanted to kind of set up a curve in a specific place, I can start playing with the equation. Okay, what about the first term? What does that do? Yeah, let's keep going. What does the x squared do?
The exponents, how much it moves. Right?
Okay, so if I do, so this is the curve, right? So we know that the last one moves it left and right. This one moves it up and down, or the other way around, sorry. The last one moves it up and down, the middle one moves it left and right, and this one, if I go like 4, look what it does. If I multiply the first term to make it bigger, it actually makes the parabola more narrow. If I make it smaller, let's say for example like 0.5, it makes it wider, right? So it kind of opens up the legs of the parabola to make it wider or smaller, depending on what you want to do. Guys, all of these things that we're talking about have names that we're going to get into later on. But at the end of the day, what I want you to think about is I'm translating a curve. I'm translating this curve, kind of in two-dimensional space. Curves are really interesting because curves can also define things like motion graphics, animations, as an example. And we'll talk about how this works later on. We're going to be using curves extensively in this semester, right? When we define how things move. Okay? Let's go to there. All right. Example 3, supplementary angles. Let's talk about this example for now. Find the measure of each marked angle in the figure. Okay, how do we do that? Help me out. Just going to zoom in. Okay. So if I want to find these angles, what is the value of x? How do I find the value of x here? Come on, we know this is 90 degrees, right? We know this whole thing is 90 degrees. How do I know what this angle is and this angle is? I want you to figure it out. And I want you to do it in your head. I don't want you to use some kind of calculator. Talk to me about how you would do it. Yes?
They both have 5, so divide by 5.
Wonderful. I love your thinking. So here's what he said. They all add up to 5, and I would divide whichever is by 5 and multiply by 90 degrees, and then you have the angle, right? I like to think about this as 5 divisions. I have 5 little pieces, right, to make up my 90 degrees, right? There's 5 little pieces here, right? 3 of the pieces are for this angle, and 2 of the pieces are for this angle, right? So if I take 2 pieces out of 5, which is, remember, what's 1 out of 5 in terms of percent? 1 out of 5. 20%. 2 pieces is 40%. 40% of 90, right? 60% of 90. 6 times 9 is 54, which is an easy way to figure that out. 54 degrees for a 3x, right? Does that make sense? So whenever we see this kind of stuff, in your mind, you should start partitioning. How do I partition? How do I create a partition scheme as a programmer? Think like a programmer, not as a mathematician is what I'm saying, right? How do I partition this in my mind to kind of narrow it down, to break it down into components that I can understand? And I look at something like this. Right? Okay, if we know that, then what is x? That's a different question. Right? We know what the values are, so what is x? How do I find x? 90 divided by 5. Okay? Because that's the partition that we're creating, right? Because if you think about this, right? If I divide 90 by 5, I have 5 equal parts. That's what x is, that equal part. Because I'm multiplying 3 times those equal parts, 2 times those equal parts. Make sense? Okay. So, in your mind, guys, don't just think math. Think, logically. Think like a Vulcan. All right. How about this one? What is x in this case? I just did it with you just now. It's the same thing. So how many parts am I taking, am I taking this whole thing? What is this equate to, this whole thing? 180 degrees, right? So 9 parts, I have 9 divisions of 180 degrees, right? So I'm going to take 180 degrees divided by 9, and that's my x, right? Just like we said before. 2 of those divisions, 2 out of 9, and 7 out of 9. 7 out of 9. For those Star Trek fans. All right. Okay, makes sense? So that's how I would figure it out. So guys, don't look at this and go, what is he asking? How do I do this? Guys, think about this. 90 degrees, 180 degrees, 207. I'm going to give you very simple things like those things. And same thing with Josh. He's not going to try when it's not about tricking you. It's about you recognizing. And one thing that we want to do as programmers is we want recognition over recall. Okay? In your mind, you should look at something and go, I know this. Right? You don't want to sit there and go like, wait, what was that again? Forget it. If you're there, it's too late. Okay? Okay. Here's another one. We're almost done. We're almost done, I swear. Okay? And I'm talking about this really quickly before I get into something else with you guys in a second is I want to find the sine, cosine, and tangent values for the angles alpha, beta in the figure below. How do I do that? I want to find the sine, cosine, and tangent, right, for these things. What set of equations am I going to use here that I showed you? I flashed up here recently over maybe 5-6 slides ago. Kind of showed you that equation. I want a relationship. I want to use some kind of rule. What rule am I going to use to figure this out? Sohcahtoa, or I can use the sine rule, right? The sine rule is pretty simple because I have a relationship between all these things. You don't need to know in your mind what the answer is. You need to know in your mind, what do I do to figure this out? How do I decouple these things that Tom is asking or Josh is asking to figure out what I need to do, right? So here's something interesting. Here's what I know. I know this is 90 degrees. And I have the lengths of the legs, right? And if I have the length of the legs, I can find the other triangles. I have some information, and from that information, I can find the other pieces of information, right? That's how I do it, okay? And the way you do that is plug it into the sine rule, which is probably going to be your best friend, this one, or Sohcahtoa, if you want to use that as well, right? Because look, I already have these things, right? A, B, C, I know those things, right? And I want to find these things. I know one of them, right? One of them, let's say C, what you see as a hypotenuse, right? C is 90 degrees. So we have some value over 90. Right there we have a ratio, right? And I can start plugging in the other values. That's what I can do, right? So it's pretty simple. And basically what you're doing is you're solving an equation, right? So how do I do that? Let's do a very simple example of that. Let's go back to that. So if I'm going to use Sohcahtoa, right, and we know that that the big C, this vertex here is 90 degrees, so this would be gamma, right, alpha, beta, gamma. So did anyone calculate for me one of the other ones, beta? What would beta be? Also, another thing to note is there a magic triangle here? Remember I said there's like these triples? Can you see something that's like relational that you look at from the very beginning? My mind doesn't seem to be something like that, right? So 36 and 85 and 77, there's random numbers that in my mind I look at them like, I don't know what those are, right? But what you can do is you can start subbing things in, right? So I know that, sine, as an example, sine over, or the number over sine, right? And that's alpha, there's alpha, right? And then there's beta. Beta would be cosine, right? So let's take a look. Let's go back to that equation again. So if you look at here, here's all sines. Sine alpha, sine beta, sine gamma, right? So it's all sines. So then how do we do that? So I'm basically saying that 90, which is, where this is, right? 85 over 90, that's what it is. 85 over sine of 90. What's sine of 90? Right? We just said it, 1. 85 over 90 is 1. It means 85. That's what it equals to, 85. Right? So one of them is worth 85. Okay, cool. We know that that's the case. And that must mean that if I go back to that thing here, that this is this part, right? So this is equal to 85. And then we have some kind of value over sine of some value, right? So how do I rearrange the equation so that I can figure out the other one of beta? If I know what b is, and then what I want to do is I want to take b over 85, and that's what equals to the sine of whatever the angle is, okay? So let's go back up. So I go back to this, and if I go b, right, which is this one here, right? B is 77. B is 77. 77 over 85, and you're going to get the value that you would get with sine of b. All right, that's how it works, okay? And that's how you sub them in. You can also use Sohcahtoa. If you like Sohcahtoa better, it's okay too, right? That's perfectly fine. But that, I'm just showing you how to do it. And it's asking you for sine, cosine, and tangent for all of the angles. So first we find the angles. That's the first part of this question is find the angles, solve the triangle, right? Once you solve the triangle, once you've done that, the next step is get the sine, cosine, and tangent of each of the angles. That's what we're asking here in this question. So a little bit more complex. Okay, so I'm telling you how to do it. I want you, I know this is a very simple, this is not part, there's no marks involved here. Take it away and do it. Like, try and do it. Like, it will take you a few minutes to do. But it's going to get your mind going on algebra. It's going to let you know how to use Sohcahtoa. It's going to, inform you how to use the sine law and everything else. Okay, so here's something else. I have a right angle triangle. I'm just going to zoom in. And it says, solve the right angle triangle ABC if A is equal to 44.25 centimeters and B is equal to 55.87 centimeters. How do I solve the triangle? Do I have enough information to solve this triangle? And the answer is, yes we do. Because we have two sides plus an angle. Once I have two sides and an angle, I can figure out the hypotenuse, right? I could use Pythagorean Theorem to figure out the hypotenuse, could I not? I could do that, right? And by the way, there's nothing wrong with using different kinds of approaches to solve your problem. Whether you use Pythagorean Theorem, sine law, cosine law, or if you use Sohcahtoa, you can kind of, again, figure out the rest of the triangle, right? Okay? I can tell you, when I look at the ratios, I look at 4, I look at 5, this is going to be something like 3. 3, 4, 5. I'm telling you, it's going to be something 30-something here, right? Potentially. Maybe not. We'll see. Okay, so that is that one. And then this is the last one, I think, which is finding length given the angle of elevation. And by the way, I'm going to show you the solutions this next week. We're going to go back here and say, did you do your homework? Did you try and figure this stuff out? Because you need to, because in your mind, I just want you to get your mind going, guys. So the angle of elevation from the point of the ground, 15.5 meters from the base of the tree, of the top of the tree is 60.4, find the height of the tree. And you're going to look at me and I have horns on my head when I ask this question, right? Because this is the kind of question that students hated when we went into math when we were young. What is this doing for you? There's some kind of obscurance, if you will, or it's trying to hide, what the question is. And what I'm telling you to do, and what a lot of students do these days, is draw it out. Start drawing it out if you don't know what it is. So let's think about this. The angle of elevation from the point on the ground, 15.5 meters from the base of the tree. Stop. So how would I do that? So I'm going to draw the base of the tree. So let's draw a simple tree. I'm just going to use my drawing tools here. So here's a tree. Let's say as an example, and then it's 15.5 meters away from the base of a tree. Okay. So again, I'm just going to kind of draw a line here, 15.5 meters, right? And it says the angle of elevation from a point on the ground, from here, from the base of the tree to the top of the tree, is 60.4 degrees. That means what they're asking is from here to here, right? This in here is 60.4 degrees. That's what it's asking, right? And then find the height of the tree. If I have this and I have this, what's this is what I'm saying. So let's label everything so we can see what I'm talking about. So if I say the bottom is 15.5, I'm just putting it here so it doesn't mess up PowerPoint. All right, here's 15.5 meters, right? And we know that this is 60.4, right? We're not going to put the degree in there. Here's 60.4. If I can actually draw this out a little bit. There we go. So that is the angle, 60.4, right? Once we know those two things, then what else do I know? I have 90 degrees, right? Because I have this. Look, whenever you look at something like this, you can clearly see there's a 90-degree angle here, right? And if there's a 90-degree angle here, that means that this is 90, this is 60.4. What's this? Come on, guys. What did the internal angles of a triangle add up to? 180 degrees. Use a calculator, worst case scenario, right? But you can just sit there and go, okay, so 90, plus 60.4, right, is equal to this, 150 minus 180, right? It's going to be something like 29.6. That's what this angle is up here. So let's just copy paste, right? And this is 29.6 up here. We've solved the internal angles of a triangle. I have a bunch of information now, right? I have a bunch of information I didn't have before, and now I can start figuring other things out. Make sense? That's how you break down a question like this. Don't be confused or irritated or afraid when you look at something. Start breaking it down, draw a picture. Okay, this is a lot of times will help you understand how to break down a problem. Okay? Last question. Okay, finding the angle of depression. Okay, let's do the same exercise here. Let me just take off my little guides here. Find the angle of depression. Find the angle of depression from the top of a 29.5 meter building to the base of a building across the street located 12.8 meters away. It's the same thing, right? But this time it's the angle of depression, not the angle of elevation. So elevation and depression. This is the building this time. Building, tree, doesn't matter, it's the same thing. And it tells us that there's a 29.5 meter building. So let's find the angle of depression from the top of the 29.5 meter building, that's what this is, to the base of the building across the street located 12.8 meters away. So there's another building. Let's draw another building over here. All right, let's make it fatter, just to make it different, right? And then 12.8 meters away, so we'll draw a little line that goes from here to there. From here, let's say, to there. And then we'll label it. That's what we normally do. So we'll say 12.8 meters, 12.8 meters, and we'll make that, sorry, PowerPoint is what it is, right? 12.8 meters, right? But it's not so bad. And this is 29.5 meters. Let's copy paste, just so I don't have to do it with one hand. I'm doing this with one hand, guys, so forgive me, please. There we go. And then this will be 29.5 meters, 29.5 meters. We have information about how this is, and what we want to find is the angle of depression. That's what we're looking at. So from the top of this thing down to this part right here. And what we're looking for is this angle right here, the angle of depression. Okay? But is it the angle of depression? Is this the angle of depression? Or is this the angle of depression? What am I asking? Is this the angle of depression up here? Or is this the angle of depression? Right? That's where people get a little bit messed up. Right? They're like, well, Tom would never ask that question because, you know what? Tom keeps it simple, and he'd probably want to make me to draw a triangle just like this. In your mind, guys, always think that. Because I'm not going to sit there and go like, I want to confuse everybody. I want people to fail. No, that's not what I want. I want you to think, right? But the bottom line is, start thinking about it in terms of simplicity. How do I break down a problem? I want to draw it out. Once I've drawn it, I can start to understand it, I can start to visualize it, and I can solve the problem. Okay? Questions around all of this stuff? Any questions around the stuff we covered? We covered what triangles are, angles, pi, a bunch of stuff. It's just a review to get your mind going on the things that we're going to be using throughout the entire semester. You're shaking your head. Does that mean that you're bored? Okay. Yeah. Is that you? Yeah. No, you're good? Yeah, I just want to make sure you're not too bored. I know this is like dry stuff. Is that a hand that's in the back there, or are we just stretching? It's a hand. No, you're not stretching. It's a hand. Tell me. Okay, no problem. So let's talk about this before I let you go for the day, because we're really at the end of the time. So why do we bother with any of this stuff? Well, if we open an application like Blender, which I probably should have opened with administrative privileges, because it's going to take some time. When we start drawing stuff in 2D or 3D, everything is triangles. And one thing that you're going to notice with your OpenGL, kind of course that you're going to be taking, is it doesn't matter whether you're talking about 2D or 3D, everything is triangles. So if we think about this, right, what I can do is I can triangulate as a modifier here. Let's just do that. So triangulate, what it does, it cuts this into triangles, right? So here is an example of this object, right? And let me just let me go back into object mode for a second. Sorry. I just want to apply and then go back into edit mode. There we go. So now notice that there's triangles. It's maybe kind of hard to see. And what I'm going to do is I'm just going to deselect all here. But what you can see is that you can see that each face of a three-dimensional shape, it can be broken down into triangles. By the way, geometry, three-dimensional geometry. We talked about this today with triangles and so on. And this will be the last thing we talk about today. What are the three things that all geometric shapes have? Every single one, especially in 3D. There's three things, three properties that they all have. We're going to come talk about this again. Three things. Talked about some of them already. So if I was going to break this down, this shape here, into three things. Yes?
Position, rotation, and scale.
That's kind of like the translation properties. But what else? That's for the actual object itself, maybe with a center, kind of point in the middle. How about vertices? How many vertices does this shape have? If it's a cube, which is what this is, how many vertices does a cube have? Right? Okay, cool. And how many edges does a cube have? 12, right? How many faces does a cube have? 6. There's a relationship, right? So whenever we talk about a geometric shape, whether it's a 2D or 3D, I'm talking about vertices, edges, and faces every single time. If I take a face and I cut it in half, of most geometric shapes, they're going to be triangles, my friends. This is the building block. I make a mesh. From a mesh, I can make a gun. From a mesh, I can make a human face. I just have to continue to subdivide my surfaces smaller and smaller with smaller and smaller triangles at different angles, and I can make any shape I want. All of your geometric shapes for any game you played, whether it was Elden Ring or the games that you downloaded and didn't play, all those kind of things, it's all founded on triangles. Okay? This is the beginning. So when we start talking about physics, I want you to always keep this in mind. Triangles are the most important thing you can know. Okay, believe it or not. And one of the tests we give people when we first do an interview for 3D graphics is get your C++ program to draw a triangle for me in three-dimensional space. Do that. If you can do that, then you understand graphics. Guys, thank you so much, and see you next week. Thursday, please keep in mind that Thursday, Joss is going to be teaching your first lab. It's very important you be there. It's worth 4% of your final grade. Thanks, guys.